what happens if you try to stop a car with help of a parachute? We're going to study kinematics of this. So we are basically trying to figure out the braking distance. If you drive a car and the engine stops, or basically no more engine, no more power from the engine, and let the car just run at a speed of V0, V0, and then pull a parachute. What is the braking distance? And we call this braking distance X. So basically from here, we can actually compute X. And this is when T equals 0, time equals 0 to times equal time T. And the calculation will be based on calculus and simple differential equations, okay? So this is basically first year university physics. Maybe people, high school students already understand this. So what do? We have to first think of the air drag. As I said, this is a simplistic calculation. It's based on kinematics and basically simple calculation where you don't have to care about the rolling resistance from the tires and any other thing like vibration that could take place. So only kinematics. So mass of the car will not play a role because we consider when the speed is V0 and then when the parachute is pulled, how long will it take? Rather, how far will it take before? We can also compute the time, but I'm going to focus on the braking distance. So we start with the acceleration, which is the main player here. It's going to be a negative acceleration. We already know from the drag force that the acceleration is directly proportional to v squared. V is the speed, basically the speed of an object through air. This is basically minus k v squared, and k is rho cdA over 2 v squared. This one is basically what is k here. Rho is at density. CD is a drag coefficient, and drag coefficient of a parachute can be found in a manufacturer, or you can actually also do computation or figure that out with help of wind tunnel. And A is basically the surface area here, which can also be taken from the manufacturer. They know exactly how big the parachute is, right? So this is it. We start from here, and with differential equation, we already know that A is dv dt from physics and calculus, minus kv squared. I will stick to k. I don't want to write all these parameters because we can insert them back later on. So dv dt equals minus kv squared, and we can do separation of variable. You get dv over v squared equals minus k dt, and then you integrate, right? Oh, sorry. I made a mistake. You can't do it. It was actually trying to test you a little bit. We have to do the chain rule here first. And that is when you rewrite dv dt as dv dx dt equals minus kv squared, and then you can see that dx dt, which is basically the speed. Then we have v dv dx equals minus kv squared, and now you can rearrange the equation a little bit. You get v dv equal over v squared by moving v squared to the left hand side, and then you get minus k dx. Yeah, this is just a simplification, right? You get dv over v, and then you integrate. And based on this situation, we integrate from when v equal v0 to v equal v, and then times, and not time here, when x equal 0 to x equal x. Why? Yeah, as I mentioned here, we start from time equals 0, which is basically when you pull a parachute or the parachute comes into deployment. So next step is basically math. You're going to get ln v minus ln v naught, and then you have minus k x only. This one can be rewritten as ln v over v naught equal minus kx, and I'm going to do little tricks here. You don't want to have minus kx, no problem. Just rewrite it as minus ln v over v naught equal kx, and because of the logarithm rules, you can actually turn this into a log V naught over V. This thing you should already know by now. Otherwise, you can see that it comes from here. You just replace or change places between the two because of the minus sign, you're gonna get this. And in the end, it's just to divide both sides with k, you get x equal 1 over k ln V naught over V, or x is given by this, 1 over k is 1 over rho CdA divided by 2, but 2 pop up in the denominator rather than that, ln V naught over V. So basically, this is the breaking distance. And V is basically the end result. If you want it to be 0, that's a tricky situation. But let's say you bring it down to about 0.5 meter per second, 0.1 meter per second. And V naught is what you can actually compute. I mean, you know it, sure. And A and CD are, of course, constant. So the conclusion from this equation is that the bigger the parachute, the bigger the surface area, the bigger the CD, drag coefficient, the shorter distance, because if you have big numbers here, you're going to have, of course, a smaller x, smaller breaking distance. And V naught divided by V, of course, it can be that if V naught is a lot larger than V, basically you have a higher speed, of course, than the desired result, the desired end speed or final speed, then it's going to be a large number. Otherwise, it's going to be a smaller number. So depend on your initial velocity, V naught, and also A and CD. Rho usually something that is constant. It cannot change from very much. It can do change from place to place and from altitude to altitude, but we just don't give it. Yeah, we don't care about it. CD, A are basically dependent on your parachute. And you can use a different size of parachute, no problem. So this is basically the physics behind it, based on kinematics and based on simple calculus and differential equation. That's it for now. If you have any question, just write it in the commentary below, or contact me somehow. And if you like the content like this, do subscribe and give a thumb up. Bye for now.